Welcome to the SciML and Fluid Dynamics workshop at this year's JuliaCon 2025. Well, it's just SciML, but it's also SciML with fluid dynamics and weather models. So if you are here to build a weather model, I'm sorry, that is somewhere else, but not this room. But we will be playing with the weather model. And you might be asking, what do you mean we will be playing with the weather model? I don't mean we, I mean we. Right? So this is going to be an interactive workshop. There will be a section here where we can play around. We'll teach you a few things, but ultimately our goal is your laptops are out and you're going to be given this a try. So what will happen here is that we will first learn from Milan about his Julia package, SpeedyWeather.jl, which is a pure Julia weather simulator, and he has set up this repository for us called RainMaker.jl, where it's set up as a challenge. Right? So the goal is effectively, there's this whole weather model of the Earth, and there's a part of this Earth that is JuliaCon. And the goal is to find the parameters of the Earth that make it so that way it just completely rains on JuliaCon. That's why we call it the RainMaker Challenge. We're here to make it rain, right? So the goal, so what we want to do is we want to have everyone be running this model and find what is this optimal point. You'll find that, doing this optimization is very difficult. So you're trying to use some things like scientific machine learning and some of these surrogate methods to be able to train neural networks. Using these kinds of techniques will make this process more tractable to be able to find very good, make it rain solutions. And so we're going to teach you about how to do some of these surrogate methods. We'll introduce some of them to you, and then we'll let you loose. And the goal is there's actually a leaderboard on one of these Git repositories. So you'll create a pull request that is your code for how you got your parameters, and then it will run all of them, and then we'll rank everybody by how good you are at Julia. Right? So the people who are not good at Julia, you'll be there at the bottom, and then the best Julia programmer in the entire world will be the person who's on the top of that leaderboard. Just FYI, when I was doing this workshop last time, I happened to be on the top right here. So there's a lot of riding on this, right? So if you really want to show your stuff, what you got to do is you just got to find parameters of the weather model that make it rain on JuliaCon, right? So what we got to learn about first is what is this weather model? How does it work? How do you play with it? How do you interact with it? We're going to get into all this before we then start to get into the machine learning, and then we start to learn, okay, now what are we going to do on this weather model? But first, let's let Milan give us his talk on this weather model. So come up here. And he's over in London right now. So instead, we will do the virtual version of him.
Hello and welcome, everyone. I'm Milan, a research fellow at the University of Oxford, where we develop SpeedyWeather, an atmospheric model written in Julia. SpeedyWeather simulates the weather on the globe and is developed as a research playground, including automatic differentiation and GPU-accelerated simulations. To give you an idea of what SpeedyWeather can do, I just want to show you some videos. Here, for example, is some humidity simulated in the atmosphere at relatively high resolution. But SpeedyWeather can also simulate more idealized flows. Here, for example, some turbulence, even though we've painted things so that they look like clouds. But you can also do things like particle advection, so you can nicely see how they are flowing around the world. We already use SpeedyWeather in teaching and for workshops, and so today we want to focus on surrogate modeling. With Chris and Danash, we ran a similar workshop at Julia.io on the Azores Islands in the middle of the Atlantic. You should definitely ask Chris about how much he loves that place and why he wants to rename it to Julia Island. But you came to Pittsburgh for JuliaCon 2025, and so this will be the Pittsburgh edition. On top of SpeedyWeather, we have built a package called RainMaker, and RainMaker is essentially injecting a rain gauge, so a little weather station, into the simulation and measures precipitation while the simulation is running. Based on that, we have formulated the RainMaker challenge, and the RainMaker challenge basically means that you are allowed to change the simulation, the model, as much as you like, with the objective to maximize precipitation at one location. And so you can, in the RainMaker package, you can look into the documentation. Everything is nicely documented there. But I thought I'd just give you a quick demo of this. Cool. So, RainMaker. We start using SpeedyWeather, and I give you a quick rundown of how you run a SpeedyWeather simulation, and then I tell you how to measure the precipitation and what the objective of this Rainmaker challenge is. Every speedy weather simulation starts with defining the resolution. We call this the spectral grid object because this is a spectrum model, meaning you have to define the maximum wave numbers that you actually resolve, as well as here the vertical layers. So this is the truncation 31 and the number of vertical layers is 8. Cool. What does that mean? We have a bunch of extensions for marquee packages, and so I thought I'd just give you a quick visualization of what that means. So if you run this model at this resolution, you can obviously go higher if you want to, but then also things take quite a bit longer. But the resolution that we're using today is this resolution where you have about a grid point every 400 kilometers. And sorry, I'm not zooming in here on the United States, but this is Europe instead. But it gives you an idea that you can resolve somehow different countries, but not really much more. Once you have the resolution object, the spectral grid, you construct a model by defining any kind of components that you like, and then you pass them on to the model constructor. And that return gives you back the model. Cool, let's do this. There's a bunch of more things that you can do. You see this all in the documentation, but just to give you a quick overview. Then the Rainmaker ingredients actually come in, where using Rainmaker and then defining a rain gauge at the location of Pittsburgh and adding this to the callbacks in the model will then create this rain gauge as a callback, which you now have injected into the simulation. And now you could initialize the model and run it for 20 days. So you see this takes about a few seconds to complete. And this is exactly where the surrogate modeling then comes in, because obviously if you wanted to do this a few thousand times or so, this would take quite a while in order to optimize this, in order to maximize precipitation. But here we've just run one simulation now, and I want to show you how to visualize the results. Once you have this rain gauge object, you can plot this, so rainmaker.plot of this rain gauge. We do skip for the first 5 days. This is for rules that are explained in the documentation. But once you execute this, you get back a plot like this. This is a precipitation meteogram for the location that we've looked at. And you can see here that in the first few days, at some point, it started raining a little bit. The bottom one is the rain rate. So it basically means within a certain 6-hour window of how much did it rain there. And then the top one is integrated this over time. And so the actual value you want to maximize is the value at the very end, after the 20 days, of the total accumulated precipitation. Here, in this configuration, it rained about 34 millimeters. And you can see that there's actually many days in between where it doesn't rain at all, and then a few days where it does rain a little bit. The model itself is able to produce precipitation in 2 different ways. One is convection, so this is a lot of vertical motions creating. This is basically the summer precipitation that most people in the northern hemisphere experience. And then the large-scale condensation is these typical where it just rains for days on end, and this is usually a frontal precipitation coming with low and high pressure systems. And you can see here that actually most of the precipitation here is through convection and not through large-scale condensation. There's a little bit of large-scale condensation in the beginning, but this is sometimes quite interesting to see of in which ways are you actually able to create precipitation. If I now look at a map of global precipitation, then you can see, and this is now going from the prime meridian all the way over, so Himalayas are about here, Australia would be here, North America would be here, and Pittsburgh is roughly here. And you can see that there are some areas in the world where it does rain quite a lot, but Pittsburgh at the moment is not one of them. And so the question is, what can we change in this model in order to make it rain as much as possible in Pittsburgh? Cool. For this, we have formulated the Rainmaker challenge and made this whole, so that you don't need to know as much about atmospheric modeling, a little easier by simply saying, okay, can we break this down to a problem with 10 input parameters? And so we said okay, maybe you want to make the mountains a bit higher, mountains a bit smaller. You may add an additional mountain that may have a certain height, a certain size and horizontal size. at a certain location, longitude and latitude. Maybe you want to warm up the ocean a little bit. And so you could have a higher sea surface temperature at the equator. You could have a higher or lower sea surface temperature at the poles. You could also warm up the land surface everywhere in the United States. You could also warm up the temperature just in Pennsylvania. And you can, and this is an initial condition, you can increase the zonal wind in the initial conditions. So having these 10 parameters with some defaults, we have just formulated a couple of functions here, max precipitation, just take these in, and basically do the whole model setup as I did before, so that you don't need to do this. And basically just threw this all into one function here that then returns you the total precipitation that you have received, the actual rain gauge object, as well as the simulation in case you want to plot anything else. And so from under surrogate optimization, we got back that these 10 parameters, for example, should have, in an optimized way, should have or could have these values. Cool. If we now run this max precipitation function with Anash parameters, then within a few seconds we have completed our simulation and we've actually managed to make it rain 210 millimeters. So quite a bit more than we had before. If you now look at the precipitation meteogram of this, you can see that there's actually quite a share of both large-scale condensation as well as convection. There's not much happening between day 5 and day 10 that would have already counted for. So there's definitely some optimization potential still. But after about day 12, 11 or so, it really rains for about 2 weeks on end. And having 210 millimeter of precipitation is definitely a really, really heavy flood. And I think it's probably even higher than anything that was ever recorded in Pittsburgh. Cool. And if we now look at the map of the precipitation in Pittsburgh, you can see here now that actually due to this optimization, we have achieved that there is, for some reason, a really heavy precipitation event happening right over Pittsburgh. And with that, I will hand back to Chris and Anash to introduce you to exactly how to do this surrogate modeling. Thank you very much for listening.
Yeah, so give a hand to Milan. So, okay, so does that sound fun? Are we ready to do the Rainmaker challenge? Well, first, before we're going to do this, we're going to show you how Anaskot is the solution, so that way you can replicate this, right? So, but I think that now it might be also good to have people also know where to find the Rainmaker challenge, right? So if you search for RainMaker.jl, you will find that there is a Git repository for the challenge. And the way that we'll be doing this is the Git repository has a section in the leaderboard, and we'll show this at the end after some of this, right? But there's a section to just do a commit to the documentation, to add your code for how you or where you get what your parameters are, and it'll run it through the challenge, and it'll put you onto that leaderboard, right? So go start checking out the Rainmaker challenge.jl, RainMaker.jl, you know. And again, there's just one function, and the goal is to find the parameters to that function that make it rain the most, right? There's a climate model and everything in there, but it's abstracted away. So now thinking about this problem as there's this black box, and I want to make this black box do something. Well, one of the best ways to be able to improve this optimization process is to build a machine learning model that's called a surrogate and performing this optimization on the surrogate. So now what Anas will do now is he'll tell you about how he built this solution and what ways to think about building surrogate models.
All right, let me just pull this up here. You guys can hear me fine? Cool. All right, so forgive me earlier, I was kind of giggling to myself gleefully because yeah, I was pretty proud of the solution itself. I mean, I'm not a weather model expert at all, and it was absolutely hilarious that you know, we gave the people of Pittsburgh about 5 days of calm and then torrential rainpour for about 2 weeks. 200 millimeters is quite a bit, considering that the when I looked up online, the average is usually around 17 millimeters. So pretty funny to have that kind of world domination power, and hoping everyone here will also be able to build something like that as well. What I'll be going through first here is I'd like to introduce surrogates at a high level and give people a practical understanding of how do you build surrogates in general, specifically the kinds that are under the category of data-driven surrogates. And the idea here is to build enough intuition so that when we get into the challenge, you have enough kind of working knowledge to not only build something up front that's useful, even if you're not a climate scientist, but also be able to debug it and improve it as well. And really, one thing I'd like to mention is that, in my humble opinion, surrogate technologies are paradigm shifting if done right. But the difficulty is that it's not trivial to build a good surrogate. And our hope today by this end of this workshop is to at least give you enough tools to embark on that journey and understand that it's very much possible, and it is certainly a technology that people should engage in. So what are data-driven surrogate models? Simply put, you can think of as high-fidelity representations of some kind of process. It could be a dynamical system. It could be an optimization problem. In this case, we're titled CFD surrogates, so obviously we're creating a surrogate of a CFD model. But in any case, you can make it, a surrogate can be for any process itself. And the key thing here is that data-driven surrogates have a performance that is strongly correlated with data. And we'll go through the intuitions of each part of the pipeline for how you generate a surrogate. But the key thing about it is that it's many times faster than the original model. And this in of itself is kind of hard to conceive. If someone told you something is 1,000 times faster, it's kind of hard to wrap your mind, well, what does that translate to practically? And right, you can go from something that can take you a month to not even a sitting moment inside of your chair. And the speed is absolutely incredible. And but of course, with speed, there must come accuracy, and that's kind of the whole name of the game in terms of when it comes to building a surrogate. How do you do this properly enough so that it's reliable in its use in the way that you'd like to use it, but it still has the properties that everyone loves it for, which is the speed and robustness. So what I'd like to do is, at a high level, I'd like to break down for people what exactly is the pipeline for generating a surrogate. And for the most part, the pipeline is pretty intuitive. It's very similar to any model you generally build. But in particular, we'll be diving into each part and kind of attaching the intuition of how do you do each part well enough so that the whole process in of itself comes together and gives you a surrogate that actually is incredibly useful. And there's a few points along the way that I'll make sure to bring up in order to kind of help cement the intuition. But as you can see, apologies if the colors aren't showing as well, but the first two is you have your input space. So typically you start off with, in our case, we had the RainMaker challenge, for example. We had the mountains, the temperature. All these are parameters that we have bounds for. We call this our input space. And then we sample it in some way. We'll talk more about that later. And then obviously we simulate each sample. We pass this through a model to get some kind of prediction. We optimize that model to get better predictions. We validate it by looking comparing it against data that it hasn't seen before. And of course, if it's met our criteria, we're good to go. If it hasn't, which almost certainly on your first try it won't, then we resample and we continue to kind of increase the space. And that's all there really is to generating a surrogate. So at a high level, it's actually quite easy to understand. But of course, when you dig into details to make the magic happen, this is where the challenges come from. And so one thing that I'd like to kind of offer everyone here is a kind of mode of thinking when it comes to surrogates itself. And broadly to kind of summarize it, if you look at the different parts of a surrogate, the training data, the network, the architecture, it says neural network here, but it could be any architecture, the optimization process, the improvement, in the end, what you're really trying to do is you're trying to build an emulator. And you have examples of the desired behavior of the emulator, and then you have a parameterized representation that can extract that behavior when you optimize it in order for it to emulate the simulator that you're trying to use. And then obviously you have a feedback loop that tries to improve it. And on the last column here, you can see different examples that are more tangible towards the CFD community in terms of what the training data is, high fidelity snapshots. In the architecture scene, you have everything from like your DMDs to your FNOs, Fourier neural operators, for those who aren't aware of the acronym. And of course, when it comes to optimization, how you train it, the techniques that go into having a well-behaved optimization problem so that you can have a surrogate that can be trained well to meet your criteria and needs. And then obviously at the end, we have our improvement, which I'll go into much more detail later. So let's start off with data gen. Data gen, pretty straightforward. I try to keep the examples tangible for the actual RainMaker challenge. Now, data generation is a kind of two-stage process. There's the first part where you get your original data to start your surrogate training, and then afterwards you have the resampling process. So this particular slide is talking about the first part, which you generate your initial data set. And like I said earlier, you have a bunch of parameters. As you can see here, the mountain height, mountain size, temperature of the equator, et cetera, and you have some bounds that you are interested in using your surrogate in, and then afterwards you sample them, many different kinds of sampling algorithms. Chris will be going through that in the next part. Just as a quick reminder, my part is to give you the high-level intuition, and then Chris's part is going to dive deep into the SciML ecosystem and show you all the different actual surrogates that you can use themselves. But then obviously the key thing about data generation is that once you get all your samples, you want to distribute your compute. You want to parallelize as much as you can so that you can generate the data up front. The real question, a practical question that most people ask is, well, how much data do you need up front before you get started? And it's a hard question to answer. It mostly depends on how large your parameter space is, how much do the dynamics vary, or the actual variance of your data is in that space. It's not a question that has an immediate answer to, but starting off big is good enough, because the key thing here is that you're never going to stop at your first data set. You're always going to improve it. Because most of the algorithms that you're going to be using to sample try to fill space, so to speak. And as that will turn out, it's actually, that's not, when it comes to generating surrogates, that in of itself sometimes is not enough of a criteria to get a good starting point. And the reason being is because in your parameter space, you can have pockets of dynamics that are very different than everything else. And it's a very tiny pocket. So if you uniformly sampled your space, then what ends up happening is, the rest of your space looks kind of similar, but there's this one small space that doesn't look similar at all, has a whole bunch of different dynamics. But since you're uniform sampling, that part only has its share and no more. And technically, relative to the rest of the dynamics, it's actually underrepresented. So a lot of subtleties here in terms of like how you actually generate your data and do so well. But the point is that fear not, your first data set isn't a big deal. The improvement that comes later is actually what's going to fix everything later for you. I hope that makes sense for everyone. And feel free to ask any questions along the way, please. Cool. Going into the intuition. So what I want to do here is, along the way, every time I'm going to introduce initially the pipeline at a high level, and then I'm going to try and give you some tidbits of intuition to help cement these ideas in a practical sense, so that when it comes to building these surrogates, whether it's in this challenge or outside, you have the main common working knowledge in order for you to be an effective practitioner. So I'm going to start this off with the example of how data interacts with these data-driven surrogates, and the key kind of idea that I want to drill home. And the TLDR, or take-home point, is that data is your signal in the data-driven world, right? What you see is what you get, is what I'd like to kind of really hammer into people. Now, of course, those who are neural network practitioners, those who are surrogate practitioners from the days of basis expansion functions and stuff like that, you can have good inductive biases that can help you get around the small data limit. But for now, I'm talking about data-driven surrogates broadly. So this intuition applies in that sense, just as a form of clarification. So what we're going to do is, on the left here, with the colored surface, it's just going to be a surface that I want to perform regression on. The middle is the data points that I've sampled. And then the far right is just a randomly initialized neural network that I just plot, and I see its surface. And the basic idea that I want to show is that when I train this random neural network on this data, and then I plot it over the original surface, you'll see that where the data was, we fit. Right? Where the data was, we fit, but where we did not have data, we did not fit. Right? And yes, you can regularize and kind of get away with a little more smoothness, and or you can use really good inductive biases that are not just a random feed-forward network that can help make a statement about the rest of the space that it hasn't seen. But as a purely data-driven idea, you can see that in this sense, data is your signal, and if you don't have what it is that you're trying to model in your data set, it's not going to be modeled by the surrogate properly, and so any kind of inference of the surrogate in that actual space is not going to work out. And so here's an example where I tried to increase the size of the network, and as you can see, the surface that's fitting is rough. There's more representation capacity, but it hasn't actually fit those parts that didn't have any data for. Right? So there's no free lunch in this sense. It's very important that the kind of cornerstone of these data-driven surrogates is the data set. And really the cool thing about simulators and whatnot, which is actually in the deep learning world, you don't actually get to have simulators as you do in the modeling world. So having a CFD simulator that you can kind of query as much as you'd like is not a benefit that you see elsewhere in different domains. So it's kind of unique to the modeling world. But of course, the challenge that comes with that is that the simulators are usually really slow. So then, again, you don't really get a free advantage, but certainly a better start than most in terms of other domains when it comes to deep learning applications. So then, obviously, we go ahead and resample the surface more clearly, more densely, and then obviously the smaller network is able to fit all the regions nicely, and you can see that even bigger network has done so well that this term that we use at work called line over line, LOL, which has other meanings, but in the modeling world, it certainly means we're doing a good job with a smile. Yeah, so the key thing that I wanted to very briefly mention is that just looking at this very quickly, notice that this is not perfect, right? There are clearly parts where it's a little off. But the key thing that I wanted to kind of invite everyone to understand and ponder over is that if I took this surrogate and I did optimization with it, you can see that it's captured like the properties of the manifold really well, right? Where there's a max, where there's a min, the curvature, et cetera, et cetera. And so even though it's not 100% accurate, it'll still be incredibly useful. And remember, this thing will be 1,000 times faster than the original model, sometimes even more, depending on the actual speed of the model versus the speed of the surrogate. And so, the key takeaway home here, key takeaway point that I want to make sure people understand is that just because something's not super accurate, it does not mean that it's not useful. And this is kind of a key thing, because a lot of times people think, I need something that's exactly the same as the original model. Do you, though? And this is the kind of thing that I want people to think over. So that's the intuition for data. Now we get into architecture. I'm going to go into two different classes. The first are the deep learning architectures. These are the ones that like the fancy, shiny objects that currently are taking over the space and have a lot of potential to bring a new future for us. But as it stands right now, there's still a lot of work in the space to actually make these things work at the level that some of the older techniques do as well. But what I wanted to kind of point out is that the intuition behind these models, and the reason why they're so effective is that what you do is you kind of pick a modality of a feature representation that's data-driven and parameterized. And then you just kind of throw an optimization algorithm with it, and it's able to learn the actual patterns. And what I have here on the screen is just to show an example of the different modalities that can capture different data modalities. The first is, the left one is a convolution. I'm sure people are aware of this, the ability for it to capture local spatial features. And then on the right is an example of how a feed-forward network, what it looks like in terms of how it fits a surface. So you can see when you play around with the parameters, it basically partitions the input space and starts to like raise and lower these, I guess you could say primitives that kind of fill the space or fit the surface, so to speak. And that's really how the feed-forward network is actually fitting that surface that you saw earlier based on the nodes that are inside. So I hope that's an intuitive kind of a feel for how these things work. And these are descriptions that are brief and intuitive, and I may have overstepped from the technical perspective, but as a means to massage the idea in your mind for how these things work intuitively, these are great visual demonstrations. Obviously, the next class are the basic expansion architecture. These are the ones that your DMDs, your EDMD, your generative additive models, et cetera, your radial basis functions. Chris is going to go through a lot of these that are in the literature. But this is also another class of surrogates that has the ability to do very well as well, because your basis expansion is one of those things where you can introduce a lot of domain knowledge. And with that as well, you can get a lot of generalization that might be a little more hand-holdy and harder to get with a neural network if you're not an expert practitioner. So the key idea that I wanted to go over in terms of intuition, at least for neural networks, this is a very famous image that came out back in the days when convnets was still a big thing and we didn't really know what a transformer was, and cat images were all the rage. In terms of saying, hey, this is a cat, this is a dog. And when you take the convolutional neural network and you look at its features, you'll notice that what ends up happening on the inside is that there's kind of this hierarchical representation of smaller, simpler features that compose into more complicated features as well. And this is actually an example, when you do this on fluid models, although admittedly, the image on the left is not as convincing as the hierarchical images, but it shows a basis of features that are being learned in a hierarchical fashion. And of course, on the right is an example of like these kind of basis expansion ideas or decompositions, where you take your flow feed or your data feed that you have available to you, and you kind of break it down into its modes that through a linear combination can reproduce the original as well. So these are just kind of intuitive descriptions of how these things create data-driven representations for you that can be used to create a model. Okay, cool. Optimization. I don't even know how well I'm doing for time. Okay, cool. So, optimization. I'm going to go through the two basic parts, two kind of ways that, based on the classes of surrogates that I mentioned earlier. The first being for deep learning. I know people are aware of this. In terms of backpropagation, the key idea here is that you have a bunch of data, you pass it through a network, you have an objective that measures it against the ground truth, and then you backpropagate through the chain rule in order to identify the gradient or update per weight. And we'll talk more about this later, but the idea is that as this is happening, you're monitoring your loss for your, which is your objective between your training and your validation. And the key kind of secret here that I want to mention is that most people who interact with neural networks who aren't kind of practitioners Generally, this turns into a kind of stirring competition of different hyperparameters until something works. But what I'd like to do is, I'd like to hopefully give people a pragmatic way of thinking about these things so that it doesn't turn into a, let me just throw a bunch of hyperparameters to it, but you can tangibly understand how do we get to our next incremental improvement? How do we take what's currently not learning and make this thing purr and give us a surrogate that will actually behave in the way that we'd like it to? Now, of course, just like we mentioned for the deep learning class of models, there's also the basic expansion optimization, which for the most part turns into some kind of linear solve, although there are variations of this kind. But just briefly kind of wanted to bring this up. This is usually a technique that's more well-known and something that you kind of learn in linear algebra in university versus doing chain rule for backpropagation on a neural network. Now, the cool thing is, and I'd like to mention this, is that these kind of linear solves, they actually have theoretical guarantees under certain conditions for even finding something like the global minima. But the neural networks don't, since they're nonlinear. And you have the universal approximation theorem, which basically says, hey, there's a needle. And then you kind of say, well, where? And the whole task is for you to try and actually find that supposed set of parameters that lets you arbitrarily approximate your function to whatever degree. And that's really the hard part of neural networks. Any questions so far? It seems like we're doing pretty good. Yes? Yeah, certainly. So, I mean, the question kind of has two parts. First is, if you're only going to use your surrogate once, does it make sense to kind of go through the process of, if you're only going to perform this optimization procedure once, like, whatever we're going to do now, does it make sense to build a surrogate? If it takes a super long time, no, not really, right? But the point is that in practice, when you build a surrogate that's useful in a large enough parameter space, you'll use it for all kinds of things, and repeatedly as well. It's not just going to be a one-time thing. And in that case, you make up for your loss. Also, as much as simulation time might take a lot, you have all kinds of strategies to parallelize and make this thing really generate data in a timely manner. All kinds of compute available, especially in the day and age. So, the idea of having to generate data up front as being a cost, it's certainly something that's a cost that you can eat. And I think Chris has another point on this as well.
Yeah, I think that there's two things to mention. One thing is that if you are doing these kind of sampling processes, like quasi-Monte Carlo processes, right? Then basically what you end up doing is just saying, oh, run the simulator at these independent points, which is naturally an embarrassingly parallel problem, right? So even if it can be difficult to figure out how to parallelize the model, or your model is parallelized, you can always just say, run this parameter here, this parameter here, this parameter here, this parameter here, and just give me back the data, right? So it's a nice way to be able to split up a problem to make it a bit more tractable. And then the second part, which I think Anas kind of touched a little bit earlier on, is that from relatively few samples, you can generally build a simple enough, like a representation of the manifold on which the optimization can do well, right? And so you don't need something that's necessarily good to give you the correct values, but you need to make sure that the minimums are in the same places and the maximums are in the same places. And as long as that's relatively true, you can run the optimization on the surrogate and figure out what the optimal parameters would be, even if the optimal model is not exactly quite there yet because it doesn't have enough samples, right? So it turns out that building surrogates from small amounts of data can get you there quite quickly in comparison to direct optimization, mainly because direct optimization methods can be very difficult on non-convex spaces, and I'll talk about that a bit more. But yeah, Gaussian process optimization, that is effectively a type of surrogate optimization method. So I'll talk about those a bit more too.
Yeah, and that last point is really, really important, right? So a lot of people are under the impression, well, maybe I have to sample this thing so densely enough that it's going to be, give me a kind of accuracy to be useful. But it turns out that we actually kind of, to some degree, overestimate how much we actually need in order for us to get something useful. For example, in this RainMaker challenge, the entire process of generating data to building a surrogate was about 40 minutes versus, I think, the global optimization for the RainMaker challenge that got #1, I think it was like several hours. So, getting third place for 40 minutes versus 4 hours, you can kind of see there's so much on the table that you can benefit from. And if you're just willing to eat that cost for even more difficult and realistic challenges, you can go a very long way. Okay, cool. So this is a kind of a little comic. You know, I'm a big fan of Winnie the Pooh when I was younger. And you know, the difficulty when it comes to optimizing these models, and they're so large, is that, well, there's so many parameters to deal with. So the real question is, you know, how do you navigate this space practically? It's like, I have to be able to, my task as a person after taking a model is how do I find the right numbers? And there's about 24,000 of them, right? So it gets a little out of hand. But the key thing that I want to kind of summarize for everyone, and I know people here have a decent enough background to kind of already know this, but for folks at home who don't, the key idea in the end when you're trying to kind of optimize your training is that it kind of falls into three categories, right? The first is that you have some kind of landscape that represents all the different evaluations of your objective given values of your weight. So the image on the right is an example of you know, a network that only has 2 values in its weight, and then 1 is the loss function. And then there's the idea of where you start, and there's an example where you can start in different places and then optimize, and you can end up in different places in terms of where the optimization ends, because depending on what your depending on how you traverse as well, there's probably, this is an example of gradient descent where you can get stuck in local minima versus something like a global optimization method, which will let you kind of free yourself from the basin and look around elsewhere. So yeah, this image is specifically for gradient descent, but the key idea is, what is your landscape? Where do you start? How do you traverse it? And that's that's kind of the broad idea. And as much as this is kind of an intuitive way, it's also not practical, because in practice, in a 24,000 dimensional space, how are you going to see your lost landscape? Right? You can't. Now, there are techniques that let you visualize and do projections and whatnot, but the key thing is that what I'd like to do next is, for each of the classes of surrogates that I was talking about earlier, I'd like to show you, instead of trying to reason about the lost landscape directly by visualizing it, there are proxies that lets you understand your model in a manner that can connect back to the lost surface intuitively. So for neural networks, the first one is the gradient distribution. Quick question, just show of hands, how many people have actually gone through this process of training a neural network and debugging it by plotting the distributions of the gradients for every layer? Okay. Well, you're on my team, so of course you would. Anyone else? Okay, cool, beautiful. So, one statement I'd like to make, and it's rather bold, but if you go through the literature, you'll see for yourself, is that the mass majority of improvements that came to training deep learning methods came from plotting the gradient distribution of your neural network for each layer, and basically determining different kinds of techniques that would allow this flow to be healthy. So I'd like to kind of explain this diagram for people to understand. So the idea is, for a neural network training to be healthy, it needs to have gradients, right? And the gradients have to have good values that are spread apart, that aren't zero, that allow for updates for the weights to happen. And you want, in particular, each layer to be roughly updating in the same way. So you want the shapes of your distributions to be relatively like, almost like a, your kind of normal distributed curve. And over time, so the axis here, if you can't see, sorry, whoops, is that gradients is going, you can see my mouse thing here, right? So this is these are actually your gradient values. This is over the epochs, whoops, kind of a teaser there, whoops. This is your over epoch, so this is what happens with your gradients over time. So every time I train over an epoch, I replot the distribution of my gradients. And you can see that for the top one, that we start off with a relatively wide distribution. There's healthy gradients, we got some flow, we got some updates. Then we go to the next layer, it gets a little more narrow, which closer to 0, which means that the updates lessen, but we still got some flow going. And then we go all the way to the second layer, and then it gets even narrower, close to 0. So is this a very healthy network? No, because in general, you want your gradients to be to have values that aren't 0 so that your weights can update. But if you look at the bottom example, you'll see that we start off with a very narrow, whoops, this thing keeps going to the next slide, good Lord. We start off with a very narrow distribution, just around 0, and then for layer 3 and layer 2, they're completely 0. And this is an example of the vanishing gradient problem, right? And these ideas of like the nature of the gradient itself is a proxy for the curvature of the loss that you're currently trying to move around. So connecting it back to that loss surface that we saw before. And so a lot of the debugging for a neural network is about how do we get these gradient distributions to be healthy for all the layers so that all the weights can update and so that you can the network can actually learn and converge in the way you want it. Right? And typically whenever you kind of get started naively on neural networks, you don't use the right initializations, you don't use the right activations, you don't use all the kind of mounting literature that people went through by kind of analyzing these gradient distributions and then figuring out the techniques to get you there. this is the kind of reason why. So for the deep learning perspective, a lot of your debugging in terms of why isn't this not training, why am I converging so early, et cetera, really comes from the analysis of the gradient distribution. So I just want to kind of put that into people's minds. And then an example of this, when I was saying earlier, is that people don't actually go ahead and plot the surface, the loss surface. But what happened was back in the days before deep learning was actually hot and everyone was using it, and it was, hey, we had all the methods that were just now one API call away, when we couldn't even train a deep neural network with 20 layers, and then the ResNet concept, the skip connection idea came in, and then that ended up allowing us to train all kinds of neural networks that were arbitrarily deep. And then later on, some researchers actually took the liberty of examining the loss function itself in terms of the landscape you have to traverse to get to value, and then you can see that without the rest. And I should mention again, remember these surfaces are high dimensional. This drawing is a projection, so it's not exactly 100% accurate in terms of what the actual loss landscape looks like. But as a proxy, you can see that the technique that actually allowed these gradients to flow and have everything actually train, when they didn't have it, you could see what the loss surface looked like as a surrogate for that loss versus when they actually did have it. So these are the kind of things that kind of end up happening. Okay. And then for the basic functions, very short slide on this because most people have enough, way more linear algebra knowledge than me about in terms of how do you actually debug these things. Of course, the idea with your linear solve, it's the solver that you're using, the conditioning of the matrix that you're trying to invert, invertibility, et cetera, et cetera. These are all things that people are familiar with that in order for you to kind of debug and make sure that you can get the surrogate that you'd like, these are the kind of points that you have to consider. But I'm going to just kind of briefly go over this. So one slide very quickly on active learning. This is the final slide before I get to Chris's part. I think we're doing really well on time. Okay, cool. Is active learning. So active learning is this process of improving. And so there's many ways to go about it. And I'd like to take one moment to explain a very simple process, which is the ensemble technique. So the idea is, well, after you're done training your surrogate and you'd like to improve it, the naive approach would be, well, I can maybe re-simulate some samples from my simulator and then use that, which wasn't in my training data, to then tell me how accurate my surrogate is. But then that would take forever because you're now in the problem of having to query your original simulator, which the whole point was that it's too slow. So the idea is that instead, you train several of these models, several of these surrogate models, and you have them instead do the evaluation. And then obviously across them, using proxy metrics like their variance or uncertainty, you can train another model for this. This is just one technique. You're able to actually get a sense about the space that you were able to train on, where you would need to typically resample in order for you to kind of reduce your uncertainty, reduce your variance of the different trained surrogate models, which becomes a decent proxy for the space itself. And this is just one of many techniques. But the idea is that you have this super fast surrogate, and you're able to actually use it to improve itself. And there's many techniques in that direction, but this is just one of them. And then what I wanted to do is show very briefly this idea of a parallel coordinate plot being used so that you can visualize the space itself. So this is a parallel coordinate plot for the RainMaker challenge. And the way you read these things is that the columns themselves are the parameters and all the different values. And what I want you to do is just pick one line and trace it. If you trace it through, every intersection of that line is an actual value of that point. So if you have a vector of 10 parameters, and you have 10 columns, then a line that traces through each one is going to be one sample, right? And then there's a metric at the end, like for example here it's mean absolute error. They'll say, hey, for this sample, this is the error that you got. And if you have a good color scheme and a decent enough surrogate, you'll notice that most of your error in this case is really low. So you can see that 0.08. But then there's all these red lines at the top that have high error, and if you follow them through, you'll notice that they're actually at the extrema of the sample space, right? And so then you would say to yourself, okay, cool. Well, one way of just even using this as a form of active learning is to go back and resample the extremas to make sure that in your next version of the surrogate, those values will be lower. So just an example of how, a visualization for that. Okay, cool. So any questions on intuition before we move on? Brilliant. Okay, I'm going to hand it over to Chris now. We're going over all the different techniques in the SciML ecosystem.
All right, who here is ready to build a surrogate, or at least start to make it rain? All right, you all are going to be pretty soon. Now, and there's probably some hands not up, and you're like, I'm I'm not sure what I want to give a try. I'm not sure what I want to do. Well, I want to give you a whole bunch of different ideas for different things to try, because it turns out that this space is very high dimensional. Not just what we're trying to optimize, but also the ways that you can work with this. So I want to give you a bunch of different ideas, and then if you want to try the Rainmaker challenge, you're like, hey, I don't know, give me, I don't know what I want to try. Well, here's a whole list, and you can just pluck something from the list, or come ask us. We can randomly pull someone from the list. Which one will do the best in the challenge? It's hard to know. They actually all have very different properties, and one of the ways for us to figure out is have a lot of people run the challenge and see what does well. So I want to kind of show a few of these different methods. The first one is one that I think is woefully underutilized, right? I think a lot of people have gone to deep learning, and they just go deep learning first all the time these days. But gradient-boosted regression trees or gradient-boosted decision trees, they're quick to train. They're fairly accurate, even on very nonlinear functions. Their major difficulty is that they're not differentiable, right? So the surrogate model itself is not differentiable that you get out of this, and it doesn't use derivative information to train. And so I'll talk about using derivative information in a second. So there's some downsides to these, but if you just have like tabular data, these things are extremely good. In fact, here's what it looks like to train a gradient-boosted regression tree, right? You grab XGBoost. You get training data set, right? You have your inputs X, your outputs Y, and you call XGBoost on X, Y, and it'll finish in like half a second, and then you have a predictor. And this thing is a high-dimensional, very good model, right? In fact, there's even a lot of papers that you'll find, like, this is not a long time ago, this is 2022. Why do tree-based models still outperform deep learning on tabular data, right? They're like, these things are actually really good, requires no GPU, you don't have to give your money to Jensen Huang or NVIDIA, where you can stay all out of that game, do everything on your CPU, and you get like 90% of the accuracy of a neural network. If you've never tried this before, try it with the Rainmaker challenge. You'll be surprised, and you'll be like, yeah, maybe I don't need to touch neural networks, right? So, this is one type of a method that you might want to look into and just kind of see, oh, how does this work? How do you do it? Have it in your arsenal of tricks. It's a good time to play with it. Another similar method is LIBSVM, right? So nonlinear support vector machines. I think before 2012, before AlexNet, there was a lot of people talking about support vector machines. Those kind of dove off really quickly. And the key thing about support vector machines is that, again, they're really quick to train. They're really quick to give predictions, much quicker in those respects than neural networks, like orders of magnitude. But the best SVM tends to not be as accurate as the best neural network, but it tends to be like 95% of the way there. And so maybe that's good enough, right? And so the way that support vector machines work is they basically just find lines that cut up your data into different parts, and then they basically just say, oh, anything that's on these side of the lines is red, anything on these sides of the line is green, or if it's a regression problem, it's anything below this line is predicting 1.0, anything above this is 1.5, right? Again, that kind of surrogate's not differentiable in its output, so you can't take derivatives of the surrogate itself, but it is a very fast model to learn and very fast model to use. And again, this kind of model is relatively trivial to train. So if you've never tried these types of machine learning techniques, I highly recommend that you give one of these techniques a try, because I think that these two techniques should be ones that you try before a neural network on every problem. I think that we're doing a lot of students, there's a miscarriage of justice by telling everyone to go straight to neural networks when such decently good training methods exist and will get you most of the way there. There are reasons to still use neural networks if you need that last bit of accuracy, but if you've never tried these, you will be surprised. Okay, what are these other things? Well, here's Surrogates.jl, and it's a library that pulls together a lot of these different types of surrogates that are based more on basis function expansion types of techniques, though there are a few neural network techniques in this interface. So Surrogates.jl is just basically an interface over a lot of these different architectures. So you give it a function, you basically just get your x values, right, which is all your inputs to the function. You get y values, so your outputs to the function. You give it lower bounds and upper bounds, and it builds this model, and then you can just ask the surrogate model, to give predictions at some spot in the space, and it'll be able to basically interpret. So you can think about it as, yeah, surrogates are just very high-dimensional interpolators. You build the model, and you can ask the model, what does it think it's going to be in that space? And this has 17 different options for these surrogates. A lot of the methods that this library is based on are things like radial basis functions or kriging. Kriging, so those who aren't in the know, Kriging is just another name for Gaussian processes. Like Gaussian processes, Kriging, and radial basis functions with Gaussian kernels are 3 different names for the same thing that are used in different communities. The reason why it has many different names is because it's found many different times to be fairly useful, right? So these are surrogate methods that work really well for high-dimensional spaces where the data tends to live on low-dimensional manifolds, which tends to be true for a lot of reality. So it tends to be a fairly good method. And again, it kind of just trains with a backslash. So these are no backpropagation, no nothing. It'll train in a few seconds on your computer. No tuning optimizers. But there's also a lot of other methods. I mean, I'll just call attention to a few of them. One of the ones I like the most actually is like Lobachevsky splines. Lobachevsky splines are surrogate models which have an analytical solution for the integral. So if you want to compute marginal integrals or something of your surrogate, this is actually a type of surrogate for which you can use an analytical solution and directly get the integrals for whatever you want. So if you want to be, for example, taking probability or calculating probabilities on your space, Lobachevsky splines are by far the best solution to do because they have this special property, right? There's a lot of different special properties to each one of these. I will not go into all of them, but there's a lot of different pros and cons for each of them. And then, only then, after you've looked at all these other methods that you can train quickly and everything, then you have the magical deep learning architecture, right? So deep learning or deep neural networks tend to be a surrogate method which you've learned that neural networks are things that can approximate any possible function. Again, all of these are all high-dimensional models that are universal function approximators, right? These are all things that can approximate any possible function. Neural networks tend to be the one that people have found that is best to be able to tune to the highest accuracy, but they tend to require a lot more tuning, right? Like architecture choices, hyperparameter tuning, you have to do this backpropagation and train it with GPUs. You will spend 10 to 20 times more, probably more like 100 times more time trying to figure out how to make your neural network train than any other methods. But there's a chance that you can make this thing be 3% more accurate, 4% more accurate. And for a lot of use cases, that has been determined to be the right choice, right? Is that the right choice for you? You can figure that out, right? Maybe if you haven't done this before, maybe try a neural network versus one of these other methods on your data set and see what the accuracy difference is. It's a good thing to play with. But they generally end up more accurate after you've tuned them, but you do have to pay the cost of, people tend to call it graduate student descent, right? Basically, you have a graduate student try a whole bunch of different neural network architectures and hyperparameters until you find the magic, and you go, oh, now I have a surrogate architecture that's good, right? Whereas, as I showed with the SVM, there's not even any 0 hyperparameters that I tuned in these things, and they're kind of more plug and play, right? But there are other architectures, right? And so if you really wanted to be in the playing mode right here, if you want to play around a little bit, get a little funky, you can try some things like implicit layer machine learning, right? So implicit layer machine learning methods are methods which use solvers in order to give you a universal function approximator, which has less hyperparameters. So for example, a neural ODE, right? You might think about it as, oh, I use this for ODEs and everything. It's also a machine learning architecture, right? It is a neural network. How many, and we say, okay, this is a neural network with 4 layers, right? How many layers does a neural ODE have? So putting a neural network inside of an ODE. Well, the number of layers that it actually has is the number of steps the ODE solver takes. How many steps does the ODE solver take? Well, that can be adaptive. It could change it. So it's naturally a way to be able to describe machine learning architectures that can change the number of layers on demand. In fact, we've actually have versions of this where it will automatically, through the properties of its ODE, trained to be a neural network that gives you the least number of layers to be accurate. So it's automatically, as part of its process, can do hyperparameter optimization. So there's some cool properties with these implicit layer methods. If you haven't tried them before, they could be interesting to use here. And again, you might have thought about ODEs and everything, and you might have never thought about using an ODE as a machine learning tool. But give it a try if you haven't done it yet. Another one is deep equilibrium networks. This is using a Newton method or a nonlinear solve with a neural network inside of it as a universal function approximator. And it actually ends up being equivalent to neural networks with infinitely many layers. So that solves a hyperparameter optimization problem. just make the number of layers go to infinity, right? It has some pros and cons though in terms of the way it trains, and so there's a lot of stuff that's going on. This is a very active field, of course. This is one field that the Julia SciML community has been doing a lot of research in, and you might want to try these techniques in this context. You know, you might have used ODEs before, but never as a replacement to a neural network or a replacement to a Gaussian process. Maybe give it a try, right? Now, again, like, you know, when I was saying, like, oh, you know, here's the deep, you know, the deep learning techniques, they take a lot more from you, right? Again, here's the XGBoost. It's like 4 lines of code, right, for the simple example. And here is the simplest machine learning training example that I found, right, where it's, you know, yeah, it barely fits on the screen. And then if someone who works with machine learning will probably say, oh, but you need to, you know, clip your gradients, you need to So very fast, you know, the way to be able to train these neural networks will grow and grow and grow in terms of complexity. So that's the downside, right? The upside is you can get more accuracy, but the downside is it could be really finicky to really optimize that training process. But what are some things that you get from some of these deep learning architectures? One of the ones I want to point out in the literature, if you haven't tried before, is gradient or Jacobian enhanced neural networks, right? And the point of this is I think really well highlighted by this picture, right? So let's say you have let's say our original model is this sine wave, right? And our data points are right here, right? If you train a neural network where you just say, okay, this is my surface, you know, these are the 3 values. I just train the neural network, and you know, these are my 3 values. It might just say, oh, your solution's constant, right? But if we instead say, hey, look, I want to learn a neural network model where at every single data point, I also want to get all the derivatives correct, right? So when I run my model, I also compute the derivatives of my the derivative of my model with respect to the parameters, right? Either Jacobian or gradient, right? And what then I could do is I can find a way to be able to say, I want my surrogate model to not only give you the correct outputs at data points, but also give me the correct derivatives at every data point as well. Notice I said that the first few models are non-differentiable, so that's not even well defined. But with neural networks, you can do this. So these are called gradient-enhanced neural networks. So gradient-enhanced neural networks or surrogates are methods that make sure that they're not only predicting the data, but also that the derivative at the data points tend to be correct. And with much, much fewer data points, you can get a surrogate to converge. This does require that you use a differentiable model. You have to be able to calculate derivatives of this model fast, yada, yada, but well, you're here at Julia, so it's a good method for you to know. I will say that there are non-neural network methods that are able to have this property. In fact, in Surrogates.jl, there's the gradient-enhanced kriging with partial least squares method, GKPLS, which is also a gradient-enhanced surrogate model. It's one that does not use neural networks to deep learning. So that's actually the GKPLS is one of my surrogates I would point to as like one of my favorites in a lot of these cases. So if you're really interested in this, I would say try out some GKPLS. It's not one that a lot of people kind of gravitate towards, but it has a lot of really nice properties. And sampling strategies. So so how are you going to sample the space, right? So I think Anas mentioned like, oh, like you can't just do, there's actually a very good reason why, if you're trying to choose all the points that you want to sample the surrogate at, right? There's a very good reason why you can't just do a grid search, and that's because you get exponential growth, right? Let's say you have, you want to take 10 points, you want to cut up your dimension in 10 points, right? In one dimension, you take 10 points, right? If you then have a grid, a 10 by 10 grid in 2 dimensions, it's 10 squared, so you have 100 points. If you want to then have, if you have 3 parameters and you want to do a grid 10 across in each way, then it's 10 cubed or 1,000 parameters, right? Let's say you have 30 parameters. That's a reasonably sized model. If you want a grid of 10 things in all 30 directions is 10 to the 30th power. Grids don't work, right? Grids are not an idea that extend to very high dimensions. So what can you do to extend to high dimensions? You can use some sampling techniques that come from the numerical integration literature, right? And these are called low discrepancy sequences. It's almost like you're picking random points, but the problem with randomness is that randomness can clump. You can pick random points and they're the same thing. So quasi-Monte Carlo methods are methods to be able to choose random points that spaces them out more than randomness actually does. And I think the simplest way to be able to show this is to show a Latin hypersquare. And once you see a Latin hypersquare, you'll see this. So let me just draw something up on the board here. So if you've ever seen a Latin square before, the rules with a Latin square is you get to choose one square where you can only choose one per column and one per row. So let me just choose a random Latin square. There is one X per every row and one X per every column, right? This is a random sampling process, and it tends to space things out. But you know what this has as a nice property? You can do this in no matter how many dimensions. You know, if I cut everything up into 10 blocks in each dimension, it would still only require 10 points in order to do this process in higher dimensions, right? So it's a sampling technique that tends to space everything out in a way that's almost grid-like, but downsamples it in a way that is everything is naturally spaced out. And so this is one of these kinds of techniques, right? And you might think, why would I do these kinds of sampling techniques? Like, is there any real benefit? There's a benefit that can be shown in the numerical integration literature, which is there's one way to perform numerical quadrature on high dimensional functions is to randomly sample points and see whether they're in the domain, in the integral, or out of the integral, and you can prove that this converges like O of square root of n. It turns out that if you use these type of techniques, they're called low discrepancy sequences. That convergence goes to O of n, so you double the convergence rate in a sense. So if that flew right by, then basically the thing is, it's provably a better way to sample high dimensional spaces. And so quasi-Monte-Carlo.jl is a whole library of, well, okay, it has the grid sample there just as a oh, hey, look, there's a grid. But then, the other methods like Sobel sampling, lattice rule sampling, golden samples, Kronecker samples, these are these kinds of samplers that you can use to be able to effectively look across large-scale spaces in a way that is spaced out and has these nice properties. And there's some randomizations to it as well. There's details in there, but that's as much as I'll go. But one of the things they might want to ask is, what's the difference between these samplers? Oh, then maybe that's a great question to look at. You pick one surrogate, choose different samplers, see which surrogate optimization tends to do better. Maybe one of these one samplers ends up doing better. I've never actually seen someone do that comparison. Free research paper right there. So optimization strategies. So when you are doing optimization of neural networks and things, a lot of people now are very familiar with gradient-based optimization. But the issue with gradient-based optimization is it doesn't really work in these extremely high-dimensional spaces where you're trying to get global optima, right? So here's a ball where it rolled down the hill, and oops, it got stuck in a little valley, right? So if you're trying to do this optimization, like say, oh, I have all these different parameters, I want to find the parameters that make it rain the most in Pittsburgh, if you accidentally started here and use a gradient-based optimizer, you get stuck. So instead of using these methods, so gradient-based methods, or these are all known as these local optimizers, right? These stochastic gradient descent, atom, anything that you'd use in a neural network is a local optimizer. Instead, there's a different class of optimizers called global optimizers. And they have all sorts of different strategies, right? Here I'm showing you one strategy, which is a particle swarm, which is instead of having one point, you have a whole bunch of points around your domain, and you make each of them do little tiny steps at a time, right? And so you kind of have these rules that say, hey, step towards where you go, step towards a direction that's going downhill, but also step towards the middle a bit of the clump. And if you do this process long enough, they'll all clump in the same spot, and they have certain properties that they'll find the global minima. Now, the proof that they actually find the global minima is that if you run a particle swarm optimizer long enough, it will actually go everywhere in space, so therefore it will hit them optima. But so these things are not actually that great. There's a lot of not great properties with them, but they are the best thing that we tend to have. So there are globalizing optimization strategies that can do optimization on and to find global optima. They don't have great scaling to large dimensions. They require at least 100,000 iterations to start converging to something. They're unpredictable, hard to tune, and there's also no guarantee that they will give you the global optima, right? You can use a global optimizer and it'll tell you this is the value. You can never really trust that value. There are methods for guaranteeing global optimization. I will have a talk that uses them, optimal inserting quantification of SciML models. So I'll give a talk on this tomorrow if you want to hear about them. But those methods have an exponential growth in their cost. So basically, if you're going to do more, if you try to optimize a model with more than 8 parameters, those types of methods that can guarantee and certify global optima, like if you want to do 10 parameters, it's probably going to take you like 10 years to run that optimizer. So that's why we end up going to these types of globalizing optimization strategies, which particle swarms, differential evolution, they tend to be more of an art than a science, and there's a lot of hyperparameters, and you can never certify the result, but they are the tool that we have here. Right? And this is actually the kind of the key. So why do we build a surrogate method? Well, because these tend to be the best ways to do global optimization today, and they require that you run the model hundreds of thousands of times to be able to run the process. And so building a surrogate and then running the globalizing optimization on the surrogate tends to be a really effective means to do that. I will say that there's another method, which is multi-start optimization, which is kind of exactly this picture. If you run a local optimization, a lot of different places, if you're local, but you're also live everywhere, then you're global, right? Now this tends to have its own issues, right? It's unclear how to pick starting spaces, yada yada. You never know if you picked enough starting spaces, right? So, but that's also something to try. Now, what we have is as a nice tool to help you kind of explore the space of the optimization methods is Documenter.jl. I'll say that this library was actually at first called GalacticOptim.jl because it was a tool that had all the global optimizers. And so, what's more global than the globe? It's the galaxy. I thought it was a very funny joke, but everyone told me I should rename the library. So now it's just Optimization.jl, and it's not as fun of a name, but it still has all of the global optimization tools. So you can find, if you've used Optimization.jl to train neural networks before, and if you've used it before to train, SciML models, you probably stuck to, Atom, Optimization, Optim.jl. It's kept to a very small set of methods. A lot of these other methods that you might have never heard before, these are all the ones to look at for these global optimizations. And to help you out, we've actually been running a whole lot of black box global optimizers, global optimization benchmarks. We're improving these benchmarks every day, so hopefully within the next few months we're going to be publishing some more about this. But one of the things that we're doing is, so here this is a case where there's more than 1,000 global optimization problems that are non-convex. And what we did is we just let a lot of these global optimizers run, and we just said, okay, within 10 iterations, how many of them found something close to the global optimum? With 100 iterations, how many of them found something close? 1,000, 10,000. And one of the things that we found is actually this native Julia method, blackbox.optim.jl, tends to actually be fairly good, like 95% success rate. And so we're trying to find harder problems to be able to make it fail. But yeah, but I mean, you can look at these benchmarks and it kind of suggests that these are some black box global optimizers that tend to converge well, and there are some that don't tend to converge as well. But they actually, just because you pick a good global optimizer doesn't mean it'll actually work on your problem. And I'll say, go to this here. This picture's actually been improved. There's even more methods than what I show here. Now we've added that the PyCMA, so like the CMA library in Python is part of the benchmark, and we just keep on adding more and more to this as a case. So if you have a very good, hard global optimization problem, we should add it here. But one of the things that happens too with these methods is they don't actually count iteration the same. And so for some of them, the cost per iteration is actually they're calling your model or your function multiple times. So it actually can be kind of hard to do the side-by-side comparison here. We're trying to find more ways to be able to compare between them. But I'd say in general, if you want to just kind of skip over it, if you build a surrogate model, maybe just going towards blackbox.optim.jl is a reasonable choice. And you can, if you use optimization.jl, you can write your optimization problem once and try hundreds of these different methods and see which one tends to work. And we also have some really new methods that's going to be coming out in a year that are really cool and GPU accelerated, but that's a different talk. So, okay, last thing is hybrid techniques, right? What do you mean hybrid techniques? Well, if you actually go to the Surrogates.jl library, it actually has its own optimizers, right? Because actually the surrogates can tell you a lot, right? So some, for example, Gaussian processes or Kriging methods have an uncertainty estimate, right? So you can use that uncertainty estimate to say, hey, look, instead of search sampling the space like this, sample the space where follow where the Gaussian process says we have the most uncertainty in the surrogate model. Or balance that, right? Pick a point that is where we have a lot of uncertainty, but also where the surrogate model says we're getting closer to the minima. Right? And so you can come up with these optimization techniques that are very specific to certain types of surrogates. And Surrogates.jl has a lot of these techniques inside of there. And I would say that the EI, the expected improvement method, this is the numerical analyst version from the 1990s. That's the naming that they use there. These days, I think I heard it in the room already, it was Gaussian process optimization, right? But it's basically the same method, just tied with the machine learning of a bow with the new naming on it, right? And so, yeah, one of the questions that you can have is building a surrogate and then using one of the global optimizer techniques going to do better than Gaussian process surrogate with this specialized optimizer? I personally don't think that there's enough research to know. I could not point you to a paper that tells you which one does better on average on a lot of problems. So why not try it for the RainMaker challenge and see who comes out on top, right? Another interesting thing is that there's actually optimization techniques that do this building of surrogates as part of them, right? So surrogate model optim.jl is a library in Julia that uses properties of radial basis functions in order to do a global optimization process. It's similar to surrogate opt, which is a function in MATLAB, right? That does this kind of optimization with radial basis functions. So these kind of hybrid techniques that are global optimizers that are actually internally building a surrogate. In fact, I've even heard Stephen Johnson say that every global optimizer is actually a surrogate optimizer in some sense because they're always approximating some function and using the properties of that function to step forward. So I think you could even go as far as to say we're always building surrogates, and these are all just different ways of doing surrogates. But I think that I've given you a lot of ideas. So this is going to be an interactive workshop. I think it's time to make it rain. So it's time to make sure that you get your laptops out and let's pull up the RainMaker challenge and let's go for it. Right? So I can actually see that, well, Milan looks like he's the one who's most on the leaderboard right now, right? Does anyone have a submission in already? So,
yeah, where am I?
Oh. So what you have to do is you have to go to this Git repository, and you'll give a submission, right, by giving a pull request to this page. Yeah, well, I guess I'll show that in a second. Right, so you give a pull request to this page. Well, actually, the instructions are right here. Yeah, so I recommend that you take the simple function that Milan had shared. I think that we put this in the repo with the. Yep. So this shows you everything that you can do with the RainMaker challenge. We simplified it down so that way you just have one function that you could put numbers in. But if you want to kind of see everything that you can tweak, these are all the different things that you can tweak. They're all documented in the repo. And then what you do is you just follow these instructions for how to make a submission, right? So you basically just make a pull request to the documentation that says, here's my name, here's a description of what you did to give it, I did, Gaussian process regression with black box global optimization, right? And then you share your script, and what it will do is it will run the script, and it'll find out how much rain happened over JuliaCon, and then it will rank you in this leaderboard based off of the results you got. So let's give it a try now. Everyone go to the rainmaker.jl, try to get this up and running. And let me know if you have any issues. I think Anas has done this before, so we can help you out. I think Anshul was also roaming around, and he's done this before, and he can help people get started. Just raise your hand if you have any issues trying to get the RainMaker running. First thing to do is just get the repo running with the parameters in, and then figure out what to try. And again, I gave you a lot of suggestions for different techniques to do here, but try anything. You know, if you think that you want to try to do a brute force global optimization, go for it. You know, just do submissions of everything you can think of, and let's see who could get the best result here.